And thank you very much also for accepting the invitation.
Can you all hear me and see my presentation?
Yeah,
I can.
Okay, so I'll get started. So I'm Thomas Gibaud. I work at the École Normale Supérieure de Lyon in France, and I'm a CNRS researcher. That means that I mainly do research and very no teaching. So today I'm going to talk about tuning the viscoelasticity and structure of fractal colloidal gel. And the main questions that I want to address is when formulation is set, that is to say, we fix the interaction, we fix the volume fraction, everything is set. How can one tune the mechanic and structure of soft solids? And so we have recent work where we did it with high power ultrasound. So I won't talk about that today, and I will talk about shear. So making soft solid, let's start with that. Soft solid with colloids. So the interest of using colloids is that you have a fine tuning of the particles. You can tune the interactions, the shapes, the concentration, etc. And you can see colloids as giant atoms. So they are big, they are slow, they make soft structure, they have versatile interaction, and there is a huge number of states as compared to atomic solids. So that's why I, as a soft matter physicist, use colloids. So there are soft solid. I just show you 3 states of soft solid. One is crystal. So the idea here is that it's a thermodynamic state, and all the colloids are positioned on a lattice with a periodic structure. And so here is an example where those guys had colloids with directional interaction, and they can make this beautiful Kagome lattice that you see here. Another kind of soft solid is a gel. So for that, you need a dilute suspension of very attractive particles. And when you put them in solution, due to KT, they will form aggregates and form fractal gels. Another class of soft solid are glasses. So here, you are highly concentrated, and you have mostly a repulsive particle, and you can make this overcrowded soft solid, which are called glasses. So those soft solids, the main distinction between them is that crystals is an equilibrium structure. So everything is ruled by thermodynamic, meaning that the system will go for the global energy in landscape. And what's important is that the final state, which I call B here, does not depend on the reaction path. It only depends on the coordinate of the final state B. And that's very important. Whatever you do between A and B doesn't matter. It's the coordinate of B that matters. And then there are the 2 other states, which are gels and glasses, and those are out of equilibrium state. And here, the difference between the crystal state is that the path that you will choose to go from A to B does matter. So if you start from a liquid and you spend some time in a crystal state and blah, 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 B will, the final state will remember that. And that's the difference between the crystal state. So you can create, and so it's out of equilibrium. And the thing is that in the landscape here is very, there are plenty of local minimum, and the system can be stuck in one of them. And that's what gives this out of equilibrium arrested state. And you can have multiple states which are out of equilibrium. And that's why these gel and glasses are very rich in terms of structure and dynamics, especially the gel state, which I'm going to focus later on. So let me give you some example. So for example, in proteins with attractions that can be tuned with temperature, you can you can tune, so you can quench your system with temperature and access arrested phase separation. And depending on the quench rate, you can select a different size of structure, just on the rate, same final temperature, same final state. But if you quench it slowly, you'll get large structure. And if you quench it fast, you can get very small structure. So you can just tune the structure here with the rate of your quench. Another system from George group is they have a colloidal gel composed of colloidal and depletion, and they use depletion to create the attraction. And they pre-shear their system, and they can make different states. So when there is a low shear, they make this inhomogeneous structure with a low elasticity. Whereas when they use high shear, they make this homogeneous structure with a higher elasticity. And so the rule of thumb in this kind of soft solid, if you want a high elasticity, you need to have small structure, homogeneous sample, high attraction, high volume fraction. That will help you pump up basically the elasticity. And so what I want to talk about in this talk is basically what George did, but with a different system, and also in the gel limit, in the fractal gel limit. So very dilute, very attractive particle. And so to do that, this is my rheology protocol that's going to bring me my gel from a fluid state to a solid state. So I use a stress control rheometer. So let me remind you, there is a rotor, a stator, a gap. In between, we put the sample, and we can impose some strain, some shear rate, some stress, and measure the elastic and viscoelastic modulus of the sample. And so I load my sample, and then I do the following. So I do first a pre-shear of 1000 second -1, and that's basically to fluidize my sample, erase any history, and that's basically the start over button. Then I do a shear rate quench. I'm going to shear the sample for about 20 to 200 seconds to a shear rate which I call gamma dot 0, which will vary between 1000 and almost 0 second -1. And then I stop my system. And I have two ways to stop my system. Either I impose a stress equal to 0 or a shear rate equal to 0. And then I have formed my new gel at this point, and I just then do a characterization. So I let it rest a bit so that G prime builds and becomes stationary. Then I can do a frequency sweep to characterize the frequency spectrum of my viscoelastic gel. And then I can break it and do stuff like that. So the advantage of such a protocol, it's quite rapid. Within a few hundred seconds, you can prepare a new gel. The catch is that, as I said, you have the same concentration, same interaction. You have one dispersion, and with one dispersion, by tuning the shear rate quench here, you can create multiple gels. So if we have variation of the mechanical property, it is only due to the structure of this gel. And that's really what, it's a unique way, basically, to test the interplay between structure and mechanics. And the rule of thumb, as I said, a smaller homogeneous structure makes stronger gel. That's what the literature tells us. So the constraint on the system is that we have to have self-healing gels, because if you take a gel that breaks and then doesn't reform, you can't use this protocol. So that's the constraint of the system. And so the system that I use is an old system. It's called carbon black gel. It was first used by the weights group, and especially carbonic trapé. So that's the gel in question. So carbon black are sticky fractal colloids. When you put them in oil, they will aggregate and form this fractal gel. And the viscoelasticity properties of the gel are the following. So here you have G prime and G double prime as a function of the frequency. And here you have high concentration, low concentration. So at high concentration, you have a very elastic gel with an elastic plateau here. You see here the loss modulus is going to go up and eventually cross the elastic plateau here. And that's what I find interesting in this system, is that you have a crossover between G prime and G double prime. The viscosity of the system is sufficiently high so that basically the elastic response of the system is not just flat, as it is in most gel system, where you just have two straight lines with G prime on top of G double prime. Here there is a crossover, and I'm very interested in this. And as you lower the concentration, you see that the elastic plateau goes down. The crossover also is shifted to the lower frequency. And so the idea is that you can sum up the viscoelastic property of such system in this way. You have an elastic plateau, which is set by the concentration of the gel. And then you have the viscosity, which is set by the viscosity of the background, basically. And so you're going to move the plateau, the elastic plateau, on this background viscosity with concentration. And when you understand that, you can do the scaling of all this data, and you see you have this master curve, where here you have a slope of 1 telling you that this is really the viscosity, and here you have the elastic plateau. And so the question, keeping the concentration constant now with a shear protocol, can we have the same kind of scaling with shear? So the carbon black particle, I told you there is a lot of them. It's particles which are about, the primary particle are 10 nanometers. They're fused together and form those fractal particles. And you have basically a library of them, which is kind of nice, from kind of spherical guys to super fractal guys. And so the ones that I will kind of use are the small one. And I use the small one basically because at some point I want to do SACs. And SACs works better with small particles because then you can eventually measure the size of larger clusters. If you start with too big particles, you're out of the SACs range. So SACs, what is it? You shine X-ray on your sample, it's scattered by the sample, and you collect the data on a camera. There's two things I'm going to go very fast on that. There's two things which are important. It's the scattering wave vector, Q, which sets basically the length at which we probe the system, so 2 pi over Q. And there is a scattering intensity, which is proportional to the Fourier transform square of the electron density of your sample. And we are working in Fourier space. So those are two different carbon black particles in the very dilute regime. So that's a form factor. And what you see is that basically it's flat here. So you have a cutoff here, which sets basically the size of your particle. And here you have a power law, which basically sets the fractal dimension of your particle. So I'm working with the red particle, which is Vulcan PF. And those guys are quite small. They're about 34 nanometer, and their fractal dimension is very high. It's 2.9. So you have almost a sphere with a rough surface, which would be a fractal dimension of 3, or a slope of 3. So let's do rheology now. This is the flow cessation protocol. So here I started, you remember, I pre-shear my sample to erase all history, and then I do different pre-shear. So here you have a pre-shear at 1,500 seconds, which gives a stress about 1,000 Pascal. Then I do a shear relaxation. So you see that I impose gamma dot, the stress equal to 0. So gamma dot is going to go down, 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 and eventually the rheometer completely stops. So I let now at this point my sample is resting and becoming a gel. The other protocols that I can do, instead of the shear rate relaxation, so imposing sigma equals 0, I can impose gamma dot equals 0. And when I do that, you see that for very high shear, I get a residual stress in my sample, which is 0. But for higher shear rate, that's not always the case. I get some residual stress into the material. So that's probably not the best method. So in the next, I won't discuss too much this protocol, and I will focus on this one. So imposing a stress equals 0 to reform your gel after a pre-shear. And what you see is this data is quite interesting, actually. You have first an exponential decay that tells you basically that you're stopping a fluid with some inertia, and then it drops down. You have those oscillations here. Those are creep ringings. So between here and here, basically, you've gone from a fluid state to a solid state. And this creep ringing and the going away from this exponential decay tells you that you're doing this salt gel transition, basically. There is a lot, I think, to extract from those experiments. I haven't done any calculation on that, but I think there is much to understand here. Okay, so here I show you a few experiments where we did different quench in shear rate, and 1, 2, 3, 4, 5, 6, 7, 8. So we prepared 8 different gels with this protocol, and we are now going to compare their viscoelastic properties. And you see, so those are the result of those 8 different gels, G prime, G double prime as a function of frequency. What you see is that you get something similar to Véronique Trappé with that she did with concentration, but with shear rate. So we're very happy about those results. You see that G prime will drop by a factor almost 50, depending on the shear rate, and that the crossover point is also shifted by also a factor 50, depending on the shear rate. As Véronique Trappé did, you can do some rescaling that goes nicely. You have a linear scaling between the elastic modulus and the crossover frequency, which is due basically to the background viscosity, which is here. And here are the scaling parameters. So at low shear rate, you form strong gel, and at high shear rate, you form soft gel. And that's kind of of a surprise to us. That's exactly the contrary of what Koumakis observed in his gel. High pre-shear give homogeneous and strong gel, and we get exactly the contrary. So that's something that is very puzzling to us, and that's why also we get very interested into this system. So just to conclude this slide, yeah, so we can create multiple gel with a single dispersion due to shear rate. And also important, it's compatible between with Xi's work. So Xi's works is a very important paper that tells you that if you know the volume fraction, it's a theoretical paper. So you know the volume fraction, it sets the cluster size, and it sets E prime. It's one of those papers that shows a relation between rheology and structure. But that doesn't work for us because phi is set. So we're not touching phi. And according to this paper, if we have phi, we have just one G prime, and that's not our case. So what do we do next to understand what's going on? So we need some insight from structure. And so what we do is do rheosacs. So we do that on beamline ID02. That's Narayan's beamline, and that's a beautiful beamline at the ESRF in Grenoble. And the idea is that you have a rheometer and you shine X-rays through the rheometer while you do all the rheologies that you want. And you collect the scattering intensity. And so here is the scattering intensity as a function of the wave vector for 4 different flow cessation protocols. So 4 different of those gel here. So scattering here, you know, it looks a bit similar. It's a bumpy ride towards a low Q. What do you do with that? So there is still a few things that you can see right away. So first, there are some bumps, and those bumps are basically correlation lengths or typical lengths in the system. So the high Q bump, that's small length scale, and that's the radius basically of your carbon black. Then there is a second one here and a third one. So the third one is the cluster size that of the fractal gel. And that's the new thing here. We interpret this peak as an intercorrelation between the cluster. So it's a distance between the center of one cluster and the center of the next cluster. And you see that this guy is smaller. I mean, it's larger, so it's smaller in distance than this one. It means that the cluster interpenetrates. And one way to better see all this peak is to divide basically by the fractal dimension of the gel here, that we get basically it's a line under those bumps. And you clearly see those three peaks. So R0 doesn't move as a function of the pre-shear, or that the particle size, so that we're very happy that does not work, that does not move, otherwise it would be completely screwed. And then the other peak are shifted with pre-shear, okay? And that's probably why the structure, the rheology is changed, because those peaks are shifted. So at the end, we get this picture. The carbon black dispersion developed large cluster of size CC and fractal dimension DF, separated by a distance which we call CS for structure. And those guys interpenetrate. So that's the picture that we get. So I'm going to skip that, but we basically have a model to fit all of that. What's interesting in this model, since there is a constraint, because we have the same dispersion, the concentration is fixed, so that we have rho, which is this we can define as this value in our system is constant. So that's the constraint in the fit that makes us sure that we're not doing anything wrong. And that's kind of nice, because basically it's roughly a 10 parameter fit to fit something which is basically a line, so you can do pretty much whatever you want and you will fit it. But with this constraint, that makes it that makes it work, actually, and we are confident with what we're doing. So those are the results. So CS drop as a function of the shear rate. So lower shear rate makes smaller structure. That's high shear rate make smaller structure. That's good news. That's what we expected. And you see that the interpenetration, which is the ratio between CC and CS, increases at low shear rate. So at low shear rate, those clusters are interpenetrating more and more. And of course, their fractal dimension goes to lower value due to mass conservation, also all coherent. So that's the idea. Its entanglement is a key here, the interpenetration of the clusters that creates additional elasticity, and that explain that at low shear rate, we create stronger gel. So now I would like to take a few minutes just to discuss a few points. So first, I told myself, maybe here I have a superposition principle, like this temperature frequency in polymer. Is there a pre-shear frequency superposition principle? And at the end, I decided that's probably not the case, because basically I'm changing the structure of my gel. And that's against this superposition idea that you can just, by tuning the temperature or some condition, just tune the dynamic of the system, but keep everything similar. Here, we're changing stuff. Then there is shear theory. So shear theory, remember, it's this paper, Scaling Behavior of Elastic Property of Colloidal Gel. And I said it doesn't work. So that was a bit extreme. So because shear theory works for DLCA, so diffusion limited cluster aggregation, meaning that you form gel that due to Brownian motion, basically. And in such gel, you form the fractal dimension is about 1.8, 1.9. And here we have something much stronger. Okay, we have something about between 2.3 and 2.5. So we're exploring a different route than she, and that I think that's why she theory here doesn't apply actually. So it's a bit extreme to say it's wrong. It's just not the right context to apply it. And the better context would be to take into account those shear. And one result predicted by theory is that when you shear cluster, fractal cluster, they get a dimension of 2.6. So I think we're intermediate basically between diffusion limited cluster aggregation and shear induced aggregation, which exponent is 2.6. And so it's a competition between those two effects that creates our gel. And so that's what I call basically the memory effect. So it's a memory effect from the shear. It's a competition between shear and thermal energies that create those gels. So application of this principle, the one that I thought was 3D printing, because basically 3D printing is exactly this experiment. You shear a suspension, you stop it, and it will make a gel or a soft solid. So I think this is those kind of fundamental principles that we're exploring with carbon black are really pertinent for 3D printing. So to that, I will conclude. So I showed you flow protocol. I showed you that shear we can make low shear, we can make large cluster and strong gel. This is counterintuitive. The key here is that the cluster interpenetrate each other. So it's an original example, I think, where connectivity interpenetration, counterbalance, size effect. I think there are many connections to do next. Measure the conductivity of the gel, as Gibaud did. Also, there are also recent papers where they study the flow property of carbon black. Julie Ip's work in Norman Wagner's group. I think there is a lot here to do. And next, I am hiring a postdoc in Lyon in gel for 2.5 years, starting in a few months. So if somebody is interested, please contact me. And thank you for your attention.
Thank you very much, Thomas, for a very interesting talk. Is there any question in the audience? We still have 4 minutes. Does anyone want to raise a question?
Can I ask something?
Yes, of course.
Hi, Thomas. Very interesting, actually, as you might think. I have several questions. I leave some for later on, but maybe a couple now. One actually is more a comment. When you do this stress relaxation, when you go high shear rates, then you stop, you put stress 0, right? This is a quite tricky experiment. I don't think it affects your results in terms of making stronger or weaker gels, but I think these curves are quite tricky to understand, simply because at high rates you have the inertia of the tool. So one might consider just doing a very, very sudden stop, rate 0, maybe for half a second, and then put stress 0. So that is more a comment. I don't know whether you've done it or thought of it.
No, we didn't want to mix too much the protocols. But
I know, but what I'm saying is that the protocol now is anyway quite mixed, and it is technically impossible to put stress 0 without taking properly the inertia of the tool. So the tool will, even if you put stress 0, it will keep moving, and that would create.
I agree. That's basically what we see here in the curve. You see this exponential decay. That's due to the inertia. It's a combined effect of the viscosity of the fluid and inertia.
Exactly. But it's not that you follow now the stress relaxation of the sample itself.
No, it's more complicated than that. I tried at first. I was really interested in those curves, and I said, "Oh, I'm getting into complicated stuff here." So, yeah, I agree. Maybe we can discuss it, but yeah, I agree. Yeah. There might be easier protocol than the one that I chose.
That was more technical, but it's just important. The other point I find very interesting, this interpenetration. Now, is this specific to the fact that you have this carbon black, so you do not really completely break down the primary clusters, or you go to primary clusters and rather than particles if you see at different rates? So it's different from our system, where in principle you can break down to single particles. Here you would never be able to break down to single particles, right?
So if I get those particles here, so the primary particles are about 10 nanometer, and they're fused together to form this carbon black particle. So I cannot break the 10 nanometer limit. No?
Yeah.
I always have the best that I can do is I have a single particle like that.
But do you ever have something which is like that, or do you essentially get always larger clusters that depend on how?
So that's the
much
part
you
of the
shear?
talks that I did not give, and I'm not ready to give. It's basically, we did the experiments in rheological and it's time resolved. So here I presented the final state.
Yes,
but
exactly.
I have the entire history of all these things.
Yeah, exactly.
And that's why I find this work actually super interesting, the one from Norman Wagner, which is basically on flow curve. And it's how to relate now the flow curve and the structure you have of continuous shearing suspension and those arrested state when you stop shear. And I think that's the next point where I want to go. And that's become a bit more challenging because now it's relating different flowing state and stopping the flow. And so there is a huge kinetic here a huge kinetic study to do, which will, I think, be beautiful.
And maybe something for later on we can maybe discuss. In Sig theory, if I remember correctly, there are two regimes. And depending on whether the intracluster or the intercluster bonds are stronger, if I remember correctly. So maybe, and I think they give different results. Anyway.
Okay. I don't remember.
We might discuss later.
I have to...
Okay, guys, we are running out of time, so we can continue this discussion in after George's presentation if you want. I think Matthias wanted to ask something also. If it is a quick question, I think you can formulate it now, Matthias, if not at the end.
Yeah, I think it's a quick question to precisely the presentation also. That's the limit of shear rate going to zero. It looks as if you have a definite fractal structure there, fractal exponent in your analysis then at the end. Is this an understandable limit? So where you
shear equal to zero? No, I don't understand, I think, Matthias, your question.
Go to your last slide, or second but last slide, please. No, one back. Yep, here. So here, the limit of shear rate going to zero in panel C. Do you know this limit, what's going on there? These are then understandable structures that you have. The fractal dimension can be modeled by some mixing model or something.
So for the moment, I didn't present any model, but we have a toy model, but it's basically based on the sac structure. So it's not self-sustaining. It's just we built something out of the CC and CS and DF, and we do it. And I think the lower shear is the most understandable, actually, because it's a closer, you're getting towards DLCL limit. I mean, not
that
yet
is
there.
what I'm wondering. Yep.
That's where you're giving more time for the system so that Brownian motion basically can take over shear.
Okay.
That's how I see it anyway.